Yeah. Okay. So what I will do is, let me just do a recap of what we did last time. And so what we did last time was we had built a case to view gravity from a geometric perspective. Okay. And the reason why it was possible was which was possible was the trajectory of particles with same initial condition in the same gravitational field are identical. Okay. So it implies that, okay, so geometric interpretation possible. Possible, and which means even in gravitational field, particles follow geodesic, but gravity curves geometry such that geodesics are no more straight lines. This is the basic philosophy with which we did. Okay, and then I had said that this equivalence principle there is a weak equivalence principle and strong equivalence principle. Okay, so weak one mechanics mechanics in pure gravity, same for all particles. And then the strong equivalence principle says all laws of physics are same. Okay, so that is the thing. But before we proceed, what we need to do is, I thought I will do a short recap of special relativity, and that is what I propose to do today. Okay. So what we start with is the following. Now I have considered two frames. K frame and another frame, which is K prime, which is moving with respect to K with a velocity which is constant. Okay, which is important that it is a constant. And now suppose there is an event which happens in the unprimed frame. Okay. Now, so it means that at a time t and at a position xyz, an event happens, and it can be emission of a photon. And suppose this photon is detected at a time delta t plus delta t, x plus delta y, x plus delta x, y plus delta y, z plus delta z. Then we know that delta t square into c square is equal to the square of the distance between them, because it is traveling at the speed of light. And so I can write it in this form. I can write delta t square c square minus delta x square minus delta y square multiplied delta z square is equal to some quantity ds square, which is 0 in this case. Now, the same set of events could be measured in the k prime frame. And in the k prime frame, this is the equation as before. dt prime square is equal to, I have just switched from d to delta, don't worry about it. dt prime square minus dx prime square minus oh, suddenly you have switched the terminology. D prime y, dy prime square plus dz prime square equal ds prime square equal to c. Now, what you should remember is this. See, normally, suppose we were to look at sound waves, the sound wave speed will be different in different frames. So I would have got a c prime here. Now, the crux of Einstein's relativity was that speed of light is same in all frames. And that is why, while all the other quantities are from unprimed to prime, c remains unprimed as before. Is this point clear?
Yes, sir.
Okay. And so this is the crux of Einstein's theory. And this is where Einstein's theory enters. And now we consider two events. Now, see, two were the photon emitted at t, x, y, z and detected at t plus dt prime and so on. T plus dt, x plus dx and so on. Now what I'm saying is I am considering two events. Now it can be any two events. It is not necessarily that these two events should be connected by a photon trajectory. It can be any two events. And so since it is no more necessarily connected by photons, my ds square is no more 0. Is this clear? See, because I had originally said that since it is photon, this holds. Since this holds, I take this to the left-hand side and call it ds square, which is 0. But now, since this is not the photon, we are not looking at the photon path. So now the ds square need not be 0. It can be any two events. Now, in a frame k prime, let us look at the same events. It will be ds1 square equal to c square, dt1 square, dx1 square, dy1 square, dz1 square. And in another prime, k double prime, it will be s2, this one, this one, this one. Is this clear? A setting up of the problem?
Yes.
Okay, fine. Now, you know that if it was a photon, then ds is 0. Now, suppose it was not a photon, I can always write one ds in terms of the other ds. Okay, in terms of the other ds. And let me just say that ds1 square equal to f times ds square. Now, this f is a function. Now, let us see what all can it depend on. See, can it depend on x? It cannot. Because if it depends on position, it means this transformation, this relation is position dependent. And so in empty space, all points are same. So there is no reason why there should be position dependence. And hence, this F should be independent of position. What is the other thing F can depend on? F can depend on velocity of these two frames. Now, in the direction velocity, in a space-time, if suppose this F depends on direction of velocity, it means that the space-time is not isotropic. It will be different in different directions. It means F can depend only on the relative speed of the two frames. Is this point clear?
Yes, sir.
Okay. What about others? Is this point clear? Why it should depend only on the speed, relative speed?
So the thing
Can you
about
explain that? And
Huh?
so
Anirudh, what did you say? Huh?
can you repeat
Huh?
that?
Huh. Okay, I will do that. See, what is being said is, now given any two, see, if suppose two events, if two, sorry, two events, two events separated by infinitesimal intervals is zero, it means ds is zero, which means it is connected by photon trajectory. This is clear? Is this clear?
Yes, sir.
Yeah,
okay.
it's clear.
Okay. But two events need not be, suppose independently there are, suppose at some point I flip a coin at some position and time. At another place, I can flip another coin at some position and time. There is no reason that if a photon is emitted when the first coin was flipped, then the second coin will flip exactly when the photon reaches there. There is no necessity of this kind, right? They are independent events. Okay, so what I mean is, okay, so let me draw a space-time diagram. This is, and I'll do just one time and one space dimension. Okay, so let me just make it slightly realistic. Sorry. So suppose there is an event which happens here. Say a torch is switched on. Then the photon will carry on and it will reach x2, it will be T2. So here, this will be the speed of light, the slope of this one. And so these two events are connected by a photon trajectory. But I can always have one situation where I have an event happening here and an event happening here. An event happens at x1 at t1 and another event happens at x3 at t3. It is not necessary that the x3 minus x1 divided by t3 minus t1 should be the speed of light. Right? At any two events which are happening. Is this clear?
Yeah.
Okay. So now, if I calculate ds for x1, x3, this is not equal to 0. Okay. Because it is not along because this is not along a light path. Okay. Harish, Yajil, is it clear?
Yes, sir.
Okay. So now, so I consider two such events. And for such events, as I said, this need not be 0. Suppose these two events are seen in the K prime frame, then my ds1 square will be this minus this minus this minus this. And in the K double prime frame, it will be like this. Okay. Now, suppose what I am saying is, now this ds1 and ds are two quantities. Now, suppose ds1 is related to ds2, I can always multiply it by a function and get it. Okay. I mean, given a number A and a number C, there you can always find a number B, which is got so that A equal to B into C, right? Is this, are you with me?
Yes, sir. Yes, sir.
Yes.
Okay. Now, what can this function depend on? In general, this function can depend on position and velocity. Okay. And suppose it depends on position, you have a problem because it means that the relationship between ds1 and ds depends on where the event takes place, which means all points in empty space are not alike, which is not correct. Empty space is homogeneous. So it should not depend on position. Now, as far as velocity is concerned, you know that the empty space is also isotropic. All directions are the same. It means that if the function depends on the direction of velocity, then you are in trouble because you are no more having an isotropic empty space. So it means it can only depend, oh my God, battery problem. And just 1 minute. Today, I forgot to get for my iPad and getting it. Okay, so let's just continue till whatever point we can. We'll have it a shorter one. Okay, so now it means that this F can depend only on the speed of the particle. And so I say that it depends on V.
Sis, I think you have not shared the screen.
Yeah. Oh, really? Acha. Oh, screen sharing has gone, huh? Because no, it is shared.
I couldn't see it either, sir.
Yes, no,
You can see the screen, right?
No, I can't see it.
Okay. Let me do one thing. Let me just unshare it and share it again.
Yes, it is visible now.
Okay. Huh. So now, so the F which is here depends only on the speed of the systems. Okay. Now suppose it's a minute. Yeah. Ah, thanks. Thanks. Okay. So now suppose, okay, depends only on the speed. Now suppose you have two frames. You have the, okay, now you have three frames. You have the unprimed frame, then you have frame number 1 and frame number 2. Now, if you have an event in the unprimed frame whose ds square is some value, okay, then the ds square value in frame 1 will be related by this, right? As we just saw. Correct? Hello?
Yes, yes.
Yes.
Okay. Similarly, if we see the same two events in the frame 2, it will be related like this. But now, let me look at the event in 2 from frame 1. Then this ds12, that is 1 from 2, is, wait, just a minute. I think this is some mistake. ds12, no, just 1 minute. Huh? I've done a mistake here. Just hold on.
How do you distinguish homogeneity and isotropy?
Okay. So I'll give you an example. Suppose you take the surface of a cylinder.
Hmm.
Surface of a cylinder is homogeneous. You know, I told in those lectures, right? When I was there, you take a chewing gum and put it on top. You'll get the mold. Now you can move the chewing gum anywhere you want. It will fit on the surface of the cylinder. But you try to rotate the chewing gum, it will come out of the surface.
Hmm.
Okay?
Hmm.
So that is the thing. So this is wrong. So it should be no. So okay. Yeah. So it is okay. I'll just
I
correct
think
this in the
DS1
notes.
on one side and DS2 on the other side.
Yeah. This is what it is. So if suppose from DS2 to DS1, it will depend on the relative velocity. But now you have something interesting. This depends on V1 magnitude. This depends on V2 magnitude. Now, V12 is equal to V1 minus V2 mod, which is equal to mod square, mod, which is equal to V1 square plus V2 square plus 2 V1 V2 cos theta, the angle between them square root, which means the right-hand side depends on the angle between the two directions. Now, this cannot be true in general if that you have on one side, there is no dependence on angle, and the other side you have dependence on angle. The only way this can be satisfied is when f is equal to a constant. Is this clear?
Yes.
Yes.
Now, if f is a constant, we then have f square equal to f, which means I have to have f equal to 1.
Yes.
Okay, which means that f is equal to 1. It means ds in 1 prime equal to ds in any other prime, whether or not it is connected by a photon trajectory. Do you understand this?
Yes.
Yes.
Okay.
Yes.
Now, I have found this so clearly only in Landau-Lifshitz classical theory of fields. Nobody else actually dwells on this issue of why they are equal even when ds is not 0. Okay, so this is how ds becomes 0. ds is invariant. Okay. Now, we need to connect all this to what is Lorentz transformation. So now let me consider two frames, unprimed and primed, or 1 and 2. So I have T1, suppose I have the space-time coordinates of two events, T1, X1, Y1, Z1, and T2, X2, Y1 in the unprimed frame. And in the unprimed frame, the time between them is equal to T2 minus T1, and the distance between them is this. And so the four-dimensional line element S12 is given by this. That is, 1 and 2 are the two events. Now, in the primed frame, exactly the same equation will be valid in the prime, except C does not have a prime. Since we know now that the S delta S is same in both frames, I can now write this equation here. Now, this is true for any two events, doesn't have to be for the path of light. Is that okay?
Yes.
Okay. Now, if the two events occur at the same point in the K prime frame, then L1 to prime is 0 because they're happening at the same point. So X1 equal to X2, Y1 equal to Y2, Z1 equal to Z2. And hence, this is 0. So I have C square T12 square minus L12 square equal to C square to T12 prime square. And since this is a positive definite quantity, this is greater than 0. So my S12 square is greater than 0. And if it is greater than 0 in one frame, it is greater than 0 in all frames. And these are called time-like separated events. Okay. I will come to why it's called time-like. If in the primed frame, I have two events which are at the same time and not at the same place. That is, they are two events happening simultaneously, but at two different points. Then it is T12 prime, which is 0, because they are happening at the same point. And since T12, which is 0, this quantity is minus L12 prime square. And so I have S12 square is less than 0. So this interval is complex or imaginary. So this is called space-like separated. Now, to give you an example, I mean, so what I will do is I have got this. I'll take just one space and one time dimension. And this is the path of light. Slope is equal to 1 by C because T versus S. Now, if the event is here and here, then it means that it is within the light cone. And this is time-like. What it means is I can always make a transformation and make it the time direction exactly the way I have done it here. By making L12 prime as 0, I have reduced it purely a time thing. So that is, it's a it's two events happen at the same position in the primed frame. I can always bring it to that. And since here time is far more than the space, I call it time-like. If you have two events over here is where the second thing which I was telling you comes, where S12 is less than 0. For example, if I have 2 points here, they are at two different positions, but at the same time in the primed frame. And so this is 0, this is, L12 is non-zero. And so from this definition, S12 square is less than 0 and they are space-like. Do you understand this?
Yes, sir.
Okay.
Can you repeat
Right.
it?
So what is being said is just okay. Suppose I have, let's see. Okay. I have in one frame. Okay, so this is one frame. In this frame, I have two events which happen at the same spatial position. Okay, so L2 minus L1 equal to 0. But they happen at two different epochs. Okay.
Yeah.
Now, what I can do is schematically, I can actually go to another frame where they are happening at different positions at different times, but the S12 square will be greater than 0. Because here it was greater than 0 and S12 is invariant. Okay?
Yeah.
Okay, so what it means, so this is called time-like. That is, any transformation I do from one frame to another, I'm doing in such a way that it is possible for a particle to go from one point to another. I mean, it is a time-like, it is not spatially separated. Do you get this? Maybe I should spend more time on this, but I just want to rush through this before I start that. I mean, it's okay. So, so basically, this is what it is, as I said, because, if suppose, as I said, I'll just repeat, if suppose my L12 is 0, that is, they happen at the same spatial point in prime, then this quantity is positive because this is so. And since this is same in both frames, this quantity is positive. So it will always be such that C T12 is greater than L12. And as a result, it will always be, I had made that light cone, right? No. So if it is a light cone, if it happens inside the light cone in one frame, whatever frame I go, it will remain within this light cone. It will not jump here. That is
timeless.
Yeah, so a time-like vector cannot be made space-like, and a space-like vector cannot be made time-like.
Okay.
So that is what I am trying to emphasize.
If it remains within the light cone, then it is
time-like.
Time-like separation.
Time-like, because I can always make a transformation. See, okay, just here, for example, this is greater than 0, which means T12 is greater than LT1. Sorry, T12 is greater than L12.
Yeah.
Which means that this is within the light cone. And this I can convert to something in which this I can make 0, which means it is a pure time coordinate change.
Okay.
That's what I mean.
Okay, got it.
Okay. The time. Okay. Fine. Okay. Now, So this is one thing. So now let us see what is, what is this thing like? See, so what we saw was the following. What we have seen is my ds square equal to c square dt square minus dx square. And this is an invariant. Now, let us look at rotations. Okay, in classical mechanics. In rotation, suppose I have dl square equal to dx square plus dy square. Okay, suppose I have 2D rotation. Now, this is invariant. So I can always write it. So which means that if I go to another frame, a rotated frame, I will have it like this. This is the same dl square. That is, length of an object does not change on rotation, which means I can write x prime y prime as cos theta sin theta minus sin theta cos theta x y. Right? Is it okay? I do a transpose. For example, okay. So suppose I have, okay. So suppose I write it as, okay. So suppose I take a transpose. So I have x prime, y prime equal to x, y, transpose of this cos theta minus sin theta, cos theta. And I take the product. And this is equal to x1, x prime square plus y prime square. And this is equal to x, y, cos theta minus sin theta, cos theta. And then this one, which is cos theta, sin theta, minus sin theta, cos theta, x, y. Now, if I open this out, I will get it as cos theta, cos square theta, minus plus sin square theta is 1. Cos theta, sin theta, minus sin theta, cos theta is 0. Sin theta, cos theta minus sin theta is 0. Then sin square theta and cos square theta is 1. Which means x prime square plus y prime square equal to x square plus y square. And this is what you want. Under rotation, length of a vector does not change. Is this okay?
Yes.
Okay.
Yes.
Now let us see what happens here. Now here we had both these things as positive. Situation where ds square is equal to c square dt square minus dx square. And now I have, what I do is, now since it is, see, so you have cos square theta plus sin square theta equal to 1, but I have cos hyperbolic square psi minus sin hyperbolic square psi equal to 1. There is a minus sign here and a minus sign here. See, there was a plus sign here and there was a plus sign here. So this gives an indication that just like I use cos theta, now I should be able to use hyperbolic function and get this back. And so what I can write is, I can substitute x equal to, rather, I can substitute x, y is equal to cos hyperbolic psi.
So just to mention, sorry. Sorry to interrupt. Rashika just messaged me. She's running some errands right now. So she should
Fine, fine,
be
fine.
joining a bit
No
late.
problem. Yeah, no problem. No problem. Yeah. Okay. So hyperbolic psi and sine hyperbolic psi, cos hyperbolic psi into x prime, y prime. And if I now, okay, so this is there. And now I can now write it as x, y is equal to x prime, y prime.
Which I think is cos hyperbolic y minus sine hyperbolic y minus sine hyperbolic y cos hyperbolic psi. There's
No,
two
no.
signs.
No, that is because I took the prime on this side. So psi will go to minus psi. That's
Oh, okay.
because the opposite velocity. Yeah. Okay. So this will be, am I getting it correct? I don't know. Cos square. This will be, just hold on. X cos, oh, sorry, why am I writing? What am I writing? I'm stupid. Yeah, okay. We are having it in time and x now. Okay. And then, yeah. Okay. So I have this and, okay. So now let us see. I have a C here. So I have CT is equal to cos hyperbolic psi CT prime plus sine hyperbolic psi x prime, and then x equal to sine hyperbolic psi CT prime plus cos hyperbolic psi x prime. So this is what we have. Okay. And now if I take c square t square minus x square, I will find that this is equal to c square t prime square minus x prime square, which I wanted. Okay. So when this was plus, it was trigonometric function. When it is minus, it is hyperbolic function. Okay. But now what I do is the following. I say that I consider, okay, so now as I said, now I had this frame and I had another frame. And I will look at a point at the origin. Now, in the primed frame, now this point is moving with this frame. That is, this frame is at rest with respect to this point P. So, this point P, x prime, is always equal to 0. Is this correct? Is it okay?
What can you repeat it?
Now, so what I'm saying is, okay, so let me put it this way. I have a frame which is unprimed, and I have a particle which is moving in this direction with a velocity v. I set up a frame, k prime frame, which is at rest with respect to this particle and is located at the origin. Which means x prime by the construction will remain 0.
Yeah.
Because the frame is attached to the particle, so the x prime remains constant. And since it is placed at the origin, x prime is always 0. Right? Nini, is it okay?
Yes, yes, sir.
Okay. Now, if I put this x prime as 0 here, it says that CT is equal to cos hyperbolic CT prime, since x prime is 0, and x is equal to sine hyperbolic psi Ct prime. If I divide these two, I get sine hyperbolic psi by cos hyperbolic psi is equal to tan hyperbolic psi is equal to x by Ct. And so this is basically the velocity of the particle divided by c. It means that if I compare it with the rotation, the corresponding psi which is here is what is related to this one, is what is related with v by c. So I can now write, now tan hyperbolic psi is equal to v by c. Okay. And so 1 plus tan hyperbolic square psi is hyperbolic. So it's minus is equal to 1 minus v square by c square. And this is equal to sec hyperbolic square psi. And so cos hyperbolic psi is equal to 1 by square root of 1 minus v square by c square, the famous factor of relativistic thing. Yes. And now sine hyperbolic psi will be, what is it? So cos hyperbolic square psi minus sine hyperbolic square psi is equal to 1. So sine hyperbolic square psi is equal to 1 plus, sorry,
Cos minus 1.
Is equal to cos hyperbolic square psi minus 1, which is equal to which is equal to 1 by 1 minus v square by c square minus 1, which is equal to v square by c square by 1 minus v square by c square. So sine hyperbolic psi is equal to v by c square root of 1 minus v square by c square. So now if I substitute all this, I will get this one. I will get, yeah. Ctx is equal to, this will be gamma, which is, I call 1 minus v square by c square as gamma. Gamma v by c, gamma v by c, and gamma. Right? Right now?
Yes.
Okay. And this is basically the Lorentz transformation. Okay. So you have T is equal to, Ct is equal to gamma times Ct prime plus x prime v by c, and x is equal to gamma times v t prime plus x prime. So this is the Galilean kind of a transformation tempered by the relativistic correction of gamma, Lorentz transformation. So, so the idea is that, so Lorentz transformation, now if you look at cos hyperbolic psi is equal to cos of I psi. Okay. And sine hyperbolic psi is, so sine hyperbolic psi is e to the power minus e to the power psi minus e to the power minus psi divided by 2. Okay. And this is equal to e to the power I theta with a minus sign minus e to the power I theta by 2, which is equal to e to the power I theta minus e to the power minus I theta. No.
Might I interrupt? Like, are you redefining psi in terms of I and theta?
No, no, no,
Like,
no.
what exactly are you doing?
No, I am just saying that if psi is viewed as an imaginary angle, then Lorentz transformation is just a rotation by a complex angle.
Okay.
That is what I am trying to get. See, because, I mean, yeah, that's what I am trying to get here. Because, you see, sine I theta is equal to I sine hyperbolic theta. No, okay, leave it. I mean, I think there is some confusion here. I'll just clarify this, but this is what it is. So, in some sense, this is very close to rotation, the Lorentz transformation. Is that okay?
But
Yes,
rotation
yes.
is pseudo-Euclidean, right? Not in a Euclidean space.
That's what I mean by imaginary angle. That's why.
Okay, okay.
My laptop has died. It has gone. Okay. I think we'll have to stop here then. I'm sorry today it was a bit haphazard because I had not prepared at all. I was actually all set for the talking about tensors. Then I realized that I had promised you people to teach special relativity. Okay, so I will probably, yeah. What I will do is I will just make some notes about it to get the thing straight because some confusion we had, and I will post it. And I am not sure about next Tuesday, but I will tell you. Any
Okay.
questions?
Yeah, I have one. So
Yeah.
Lando defines a quantity, like he defines dual of a tensor. Like the tensor is antisymmetric and he defines a dual for it. Why does he do it?
Okay. We will come to it because I have not yet come to tensors.
Yeah, but like, could you just tell me where does it become handy? Like, dual of a vector becomes handy when we find the norm, right? Like norm
Oh,
of a vector.
no, 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 no. Actually, it's actually um, physically the dual of a vector is very useful when you are okay. You heard of what is parity violation?
Yeah, just the reflection of all the coordinates, right? Like x2
It's
minus
just
x,
not
y2.
reflection. I mean, yeah, that's on a classical parity violation. But at a quantum level, when you're doing parity violation, then the action has is a pseudo scalar, and that involves a pseudo tensor and a tensor product.
Yeah, the scalar does not remain invariant for just normal reflections, but remains invariant for
Yeah,
all other
only for
cases.
rotation.
Huh.
Yeah. So you see, if you contract a dual of a tensor with a tensor,
Hmm.
then it produces a pseudo scalar. And
Yeah.
like particles, axions are supposed to be like that. So it is at that level which is useful. But
Okay.
otherwise, let me see. Uh, okay, so look at it this way. See the area.
Hmm.
Suppose you have two vectors, A and B. The
Hmm.
vector area is A cross B.
Yeah.
Now A is a vector, B is a vector.
Hmm.
When you do inversion, they will change sign, but the product will not change sign.
Product. Yeah.
So the
Yeah. Axial.
area vector is a pseudo vector.
Yeah. All axial vectors are pseudo scalar.
Axial vectors, yeah.
Ah, all right.
Okay. Yeah. So basically, I mean, I'll come to it when we are doing tensors. There is something called the antisymmetric tensor, which I multiply, I will get it. Yeah.
Yeah.
I mean, I want to ask something. Should we proceed with special relativity for some time, or should I just shift to tensors back?
I mean, how are we going to be really coming back to special relativity quite often? Are we going to be referring it quite often in GR?
I mean, only to the extent to which we have the line element ds square, which I already introduced.
Then I think we can go straight to GR.
I'll just go to GR then. Okay.
Yeah. Unless you just ask them what they feel.
Yeril and Harish, what do you say?
Yeah,
Yes,
fine.
fine with me too.
Okay. Okay, so what I will do is I'll just continue with tensors. You got my notes, right, of GTR?
Yeah, he sent me a chapter, correct.
Pardon?
He sent a chapter.
Chapter. Yeah, so I'm writing a book, so this is the first chapter of that.
Yeah.
Okay, so was it readable? Was it okay?
I've gone maybe like 2 paragraphs and I'm not finished it yet. I'll get back to you soon, like
Okay,
in a
yeah,
day or
because
so.
I want some feedback about it. That's why,
Yeah, it
Oh,
was
sure, no
actually
problem.
good. Like, I
Okay.
thought it was a standard reference when I read it for the first time.
Okay. So, Yeril, you do all this after your exams are over, huh?
Hi.
Okay.
Harish doesn't have exams?
No, I'm done with it. Like,
No. Yeril is having her exams till 23rd.
Oh, okay.
Yeah. Okay. Chalo.
Okay,
Bye.
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 thank you, sir.
Bye.
bye.
Thank you,
Bye.
Sesh. Bye.
Bye.